right side rectangle.
I can explain it more, but it's
Yeah,
like kind of cool. It's like a whole one rectangle of a window with 3 different distinct temperature patterns.
Yeah.
Because of like the fan, and then like the.
Oh, I see. These are
Yeah, so
the fans.
Those are 2 fans stacked on top of each other. In the middle is just a sliding window.
So this one's a bigger fan.
Like a box fan.
Box fan, and then this one's the little window fans. Yeah. So you can see that you're getting. You can see that you're probably seeing the motors right here.
Yeah. And the coldest spot is the spot between the 2.
Between the 2 right here. That's going through.
Yep. Right is just the sliding window, like.
This part right here.
No, like on the left. You move your cursor to the left, like big red spots in between it. Yeah, right there.
This one.
That's still the window, but it's like sliding window stacked on top of the back pane.
Okay.
So it's like the hottest part, I guess. I don't know if that's like isn't red or yellow's the hot or something.
Yeah.
It's all one, so I have to know that's what that is. And then the left side is just the window without anything sliding.
Without anything in that. What's going on over here? Is that?
That's I guess is that a layer?
Yeah, the one disadvantage of this particular camera, and usually what the more high end cameras will actually have both a visible, your regular camera and the thermal camera, because sometimes it's very difficult to actually see. Look at it and you're kind of like saying, I think I can figure it out.
Yeah.
But it's sometimes hard to see. We're just not used to seeing these kinds of things. Folks in the military who are analysts, they can start looking at some of these things, and they can actually, with training, you can actually start figuring out the different pieces. So, any difference between these two, or are they more or less the same?
From the top left, 32, or is it about 72?
Okay, I see. There's the yeah. I don't typically trust some of the temperatures, but that's all right. So
this is the other one I posted just now. There's one more.
Yep.
Like a person.
Yep, that's a person.
And then I have another picture. It's like the exact same, but just the top left says 95.
Okay. Yeah.
So that's like lamps. The big.
This guy.
Things are lamps. And you can see a small, like the green thing in the bottom right is a computer screen.
Okay. Yeah.
And then that's like a bed.
Yep.
And that's a person.
Yeah. So.
And like with a laptop on the left.
So yeah, and the thing is, sometimes they actually don't put, depending on the application, they don't really put a visible camera, because sometimes these are used actually in nighttime situations, and nighttime situations you really can't see anyway. The one thing I've been trying to get is a night vision type of camera. That works in a different principle, which we'll talk about in another class, in another lecture. But this one, can work in total darkness, because all it's really doing is it's taking the signal from your body or from any material, and essentially translating that into an image. Night vision goggles, on the other hand, actually use a very, very small amount of light, and what it does is it amplifies the light to the point where you can kind of see it. So that still requires visible light or some form of visible light to display that. So thermal is a different beast in general. So one of the things that a lot of people use this technology for is actually looking for leaks or water leaks, because what will happen is that water will tend to hang on to heat changes. So you can actually look for water leaks behind walls using this type of technology. And as you can see, for actual mechanism, for actual motors, you can actually see that. With regard to the laptop screen that you have here, one of the interesting things that you can actually do is run your laptop, first without it doing any computation, and then one where you actually tell it to run something intensive, and you can start measuring one where the CPU is, because that thing should pop up on your with a thermal camera. You'll start to see the CPU start like really cranking out a lot of heat, so you can actually identify where it is. And this is another thing that people use it for in assembly, is that they'll use it for quality control. they'll run circuits and then kind of look for where there might be a bad component. It's typically, yeah, exactly. Typically, if you have a bad component, it will typically run hotter than the rest of it. So this is also used a lot in analysis of engines. So you can actually start, if you're trying to study what the thermal flow of heat, this is one technology that you use. But you're right, they'll most likely people will use a much higher end thermal camera. In most situations, in those applications, you'll have much better temperature gradations. In other words, you'll be able to tell the different temperature differences a lot better than what you can with this specific camera. Also, the spatial resolution will be much better. So in some respects, you're looking at so this is somebody's face with this type of camera. For a higher end camera, you will start, there'll be higher spatial resolution, so you can start really seeing like their nose, their eyes. But this is a much cheaper camera. You don't have as many pixels. That's why you can't see as many features. But the higher end cameras, they'll actually have many more pixels, so that you can actually see the different features. So in medicine, that's what you typically want. Something that you can actually use this for. I believe that they're trying to use some of this also for detecting breast cancer. I can't recall the rationale there, but they believe that sometimes tumors will run at a different temperature because of the blood flow associated with that. And there are people actually trying to use thermal cameras to see if you're lying, because what they will do is try to see if you have any changes in your blood flow pattern in your face. So that's one of the things that people have been trying to do. Mixed success, I think, because the issue with people is the variability of not so much the temperature. Everybody has the same temperature, but the emissivity of people's skin. So emissivity is basically how well your body or how well a surface emits energy. Right? There are some things that just won't emit energy. You probably heard the term low E glass. What that means is that certain glass won't emit a lot of heat, and what it does, because it can't emit a lot of heat, it'll hang on to it, and basically you don't lose as much energy. Mylar blankets are low emissivity, right? They tend to reflect the heat back to you. In fact, if you point this camera at a Mylar blanket, you should see just basically a cold belt. It should be close to black, because that Mylar blanket, even though it has a temperature, it doesn't emit heat very well. So that's what's happening in this situation. So okay, good. We'll see what kind of images you come up with to play with the thermal camera. Okay, start with questions. Yeah.
Can I go?
Can I pass? Yeah, it's fine. You posted the stuff, so we'll let you pass. No. Yes, you have to install an app. I don't remember what the name of the app is. I think it will actually. I think when you plug it in, you just plug it in and it tells you
Just like give you a
notification of download the app. Yeah, so do that and then just play around with it. It's pretty straightforward. It's pretty cool. So, question? No, I haven't posted it yet. So you were gonna ask like, oh, I haven't done that yet. Okay. How can you what? Log out of VNC server. I believe. Let me see if I can. Oh, okay. I think what you want to do, that's the viewer. For the server, I'm trying to think. Did mine go to sleep? Uh-oh. I clicked my... Let me see if I can find that. Come on. You were listening. Keep on listening. Okay. Disconnected. All right, let me see. I think they did put just for they just put the viewer on here. They did put the real VNC viewers, so you can actually be able to use that. So you don't have to download it if you want to connect to your Raspberry Pi. Oh, I see. I lost my internet connection. That's why. Let me just prep here to find that location. Real VNC. So I think on the Raspberry Pi, I think it's going to be the same as what I'm seeing on my laptop. And yeah, I think so. This is the connection. So I think you should be able to disconnect. Yeah, so I think you click on this one and then you hit disconnect. Do you see it?
How do you get to there?
To this one? I went in here. This is so the Raspberry Pi might be a different way to get that. See if you can, if it shows up on any of your application, in the application under it's stalled. Yeah, my screen is stalled. But under real VNC, can you find a real VNC?
I'm already in season.
Okay, so you have this, and then so I clicked on this one, the person. Yep, click on that. Come on. And that's where sweet old time. Should be showing up in a few. Refresh, come on. See it on my laptop, but it's there. You go. So you would click on connections. Which don't you see the? Yeah. Let's wait until I finish the lecture, and then we'll continue with that. Okay. All right. Anand?
Question? I was doing with the examples.
Yep.
For like the data set collection example. Is it going to be a question like this? Okay. So it was basically just like converting all of them to one.
Different format. Yeah. Format.
Right?
Yeah.
And then
Yeah.
basically you can like. So are we it's more like a question of the class. Are we going to be like writing more programs like that expand on that, or since it's like the non-CS type of class, like where are we going? Just the future of the class.
For the future of the class, so it'll be mostly trying to go through and do some of those types of exercises. That one was a little, I never really liked that one because it was more of a file-based analysis.
Yeah.
The later ones will be more, you're actually, basically mimicking the code to do some of the things that are showing up in the book. So the one that's missing that I need to post is like a facial recognition application, where that's towards the later part, but I think I'll just push it forward. Is that you can actually point a camera, and there's already a trained feature set or feature class in there that if you point it at people, you can it'll start drawing a little block around the faces.
Digital camera.
Exactly, just like the digital camera. So the idea there is that you understand that there's actually a face, and that if you want to delve more into how that actually works, you've got at least a starting point to work with, so that you can start. The simple CV won't really show you how it's done, but you can go into the open CV part of it and start digging more into the mechanics of that. And the way they do that is basically they train it by having a lot of samples of faces, and because you have so many samples, you can start coming up with patterns that when you present it to a particular an image, it knows to look for that specific signature, right?
That's cool.
So in much the same way that you have red, green, and blue, now you understand what red, green, and blue is. You can now sort of go through the entire image and then say, okay, I know something's red because it has 255 values in red, but very low values in the in green and blue channels. So that kind of classifications is similar to what you would see there. And I'll talk a little bit more about classification when I actually show you some of the hyperspectral imagery. So in terms of programming, we won't go beyond what you got there, but by all means, if that's something that you want to do for your final project, you're more than welcome to move in that direction. So the goal is just for you to sort of see how computer vision, how image processing works, so that when you see it in the future, it's not going to be something that you need to get up to speed with. I mean, you'll still have to do some reading and probably some experimentation, but at least you kind of understand, an image has number of samples, number of lines, number of bands, and what data type to ask. So one of the things that you should always do with images is sort of what I went over in the last week about the characteristics of images. Those are the kinds of things that you should be able to answer whenever you get an image, and be able to answer all those types of questions. So I would suggest that for your final project, if you do have certain images, ask yourself, those characteristics of the image. And by doing that, you sort of reinforce some of of what you can do in the future when you do get a quote unquote mystery image. Somebody will give you an image and you try to display it, you're like, can't display it. And then you have to go through and sort of ask yourself, well, how big is the image? Right? How many bands is the image? What kind of data is in the image also?
Right, you're breaking it down basically.
Yeah. Yeah. So, in fact, what we'll do is we'll look at some new types of images through an application called ENVI. So,
okay, right.
So in fact, let's start that now. So actually, let me kill I was just going through and trying to remember all the different things about ENVI. So I'll quit out of this. And you're welcome to follow along. I think every PC here now, I believe, has ENVI in it. And if you're curious, if you want to follow along, you can log in. I'll give you a few minutes to log in, but you should be looking for a package that says ENVI 5.5. So if you want to follow along, if not, I'll just move forward. But so ENVI is a package that was actually created, almost a couple of decades ago by a bunch of geologists, right? Because what they were trying to do is trying to identify rocks. Why do people want to identify rocks? Because they want to understand what other resources are associated with certain rocks. So you're doing one of two things. One, you're looking for possibly oil, right? Geologists always look for some resources. Oil is one of them. The other one is metals, gold. So instead of a person walking around like a prospector, looking around on at different rocks, knocking on it, somebody had the idea of saying, well, what if we fly a spectrometer on an airplane? What is a spectrometer? The spectrometer is just a special device. When you point it at a particular object, what it does is it breaks down the light into different wavelengths. So let me see if I save that. So spectrometer, you can look this up, but the idea behind a spectrometer is that, let's see if they have this one didn't have they will basically take light and pass it through a prism. And by passing it through a prism, what you can start doing is being able to measure a signature. So if I take it as a spectrometer and point it at a plant, this is the kind of signature I will see. If I point it at soil, this is the signature I'll see. And for water, you get that signature. Now, the one thing that allows spectral signatures to what you can do with spectral signatures is that it allows you to distinguish between two objects that look very much like each other. So this is actual vegetation spectrum. If I actually took a spectra of astroturf, it will not look like this at all, right? In fact, let me search for astroturf spectrum, which I was doing. Spectral signature. So if you look at this spectral signature, this is healthy grass. So we can see in this region red, green, blue. So this is around 650. This is the red channel. This is the green channel, and this is the blue channel. All right. In remote sensing, there's a lot of signatures outside of your visual, the human visual spectrum. So if we look at healthy vegetation, this is what it looks like. If you look at astroturf, this is what it looks like in the region beyond this area. If you look at what astroturf and grass look like, they more or less look the same. They're both have this bump in the green region, which is why you look at AstroTurf, looks green. So does vegetation. But just looking at them, you really can't tell the difference between the two, right? If you look beyond that, much further out, you can actually see that the vegetation all of a sudden goes up, while AstroTurf sort of stays very, very low. So this is actually the way people used to look for camouflage in World War II. They would actually make the film sensitive to a region in this region, so you can actually tell the difference between vegetation, AstroTurf, camouflage and vegetation. Okay, camouflage will look more like AstroTurf than it would vegetation. All right, so that's how spectral signatures work. Let's actually start up ENVI and show you some examples of that. So to start up ENVI, you can go into this ENVI 5.5. There's several versions of ENVI. You can just start up ENVI by itself. There's also a programming language called IDL associated with ENVI, but we'll start that also, so just so you can see that. So ENVI Classic is what I would suggest you click on, and IDL is the language that ENVI was written in. It's very much similar to MATLAB. Okay, if you're familiar with MATLAB, you can write this. You can also learn IDL fairly easily. So this is the menu that you see for ENVI, and let's just start by looking at some images. So there's several tools that you can do here. I won't go into all of them, but just be aware that there's a whole bunch of things that you can do with remote sensing data. Some of the stuff is way beyond the scope of what we want to cover here, but I just want you to get familiar with some remote sensing data, particularly hyperspectral data. So let's open up an image file. So let's actually let's move up here and look at some hyperspectral data. Right. So what is hyperspectral data? Hyperspectral data is basically many bands. All right. So we can actually display this. And as you can see, there are a lot of bands for hyperspectral data. This is an instrument called AVIRIS, AVIRIS. It's flown by NASA over all over the globe. And what you can actually do with this kind of data is be able to determine what kind of material is on the ground, not just from three colors, not just from RGB, but also from the spectral signature that we talked about. So if we want to look at this as a color image, we can click on RGB. Right. Now the question is, what bands do you display? In this situation, we said before that around 700, 650 is usually around red signature, red signature. So we click on that. The green band is about 550. I don't expect you to memorize those, but realize that there's a range of wavelengths that correspond to the different colors. So for blue, it would be 450. Right. Now we can display this, load the RGB. Right. And this is what you would see from a visible spectrum. Okay. So we can actually go in and start displaying the spectrum. So why don't we do that? You can say Tools, Profiles, and then you can do a spectrum profile. What does that look like? Well, if you look at that, wherever I have this crosshair, you're seeing the spectrum of the entire image. So again, this is the red channel, the blue channel, the green channel, and the red channel. So what I want you to notice here is that there's actually a whole range of information, okay, beyond 750 that has a lot of structure. So if you just looked at the images, just flew a regular, your cell phone camera, this is what you would see, but you wouldn't really see the rest of the structure of that data. And that's why hyperspectral is, a lot of scientists like using it, because you can actually start measuring quantities associated with a given feature. In fact, what we will now do is convert it into a form that is used for vegetation, right? So you can kind of see that, you've got, this looks like it's grass, just visually speaking, right? You look at here, it's like the question is that grass or not? Right? You would think that it is, but you're really not sure, right? If I actually click on this, this tells me this particular type of structure tells me that's grass. It may not be healthy, but it's still grass. If I click on this area over here, to me this spectrum tells me that's kind of like soil, or definitely not vegetation. If I click on different areas here, so let's click on those small parts here. If you look at this dark spot here, it's sometimes hard to tell whether that's different from another one. But when you click on that, you can almost be certain that that's probably some kind of water feature, right? You're seeing a little bit of structure there, but grass, it's very, very distinct of what you can see there. If we click on some of these regions now, we can start determining, is that grass? Nope, it's not, doesn't have that particular structure. Another way of looking at vegetation is actually putting it in what's known as color infrared. Right? If you recall, if we click on this area, there's this high signature over here, which we want to take advantage of. So what we can do is display not from 650, 550 to 450, but we'll shift it over into this region. So we'll shift it over to 750, 650, and then 550. And if we load that, this is what's known as color infrared. And this is what actually people used to use for detecting camouflage. They basically shifted the bands so that it landed, if you look at this now, this plot right here, we shifted it so that it hits this, this edge over here, that's vegetation. Now it becomes very easy to see what is vegetation. Anything that has a red hue to it is vegetation. There are different levels of vegetation health. Some of the, as you can see now that this is a little reddish. Used to be, you looked at it, it was more dark than anything else. Well, what this does is it tells you that's probably vegetation. And when we actually click on that, you can sort of see that it has the same type of signature. And it's just that it's not as bright. So this may be vegetation that's still in the process of growing, right? And this is the kind of thing that farmers like to be able to do. They want to be able to look at an area and look at their crops and be able to say, how healthy is my crops, all right? And aerial imagery, this kind of aerial imagery will allow you to do that. Okay, it's not just RGB; it's actually color infrared that gives you that information. It also becomes obvious what is not grass, all right? As you can see, as you click on anything that's not reddish, you realize that the spectrum that they have do not match any of the vegetation spectrum. So this is something that you can always Google for vegetation spectrum, and you'll see that this is the kind of structure that you'll see for grass, right? The other thing that you can also do is actually just go through the different bands within the image. So what we can actually do is create what's an animation of this. And this kind of is sort of a cool way of looking at the data and trying to understand how it actually changes as a function of wavelength. So it's as if what we were doing here now is we're going through and just running through this, the different wavelengths here. So this is actually a good visualization because it sort of tells you what's going on in the different wavelengths of light that you're seeing here, right? Sometimes you'll see something pop up, all right? And in some of those situations where it actually all of a sudden like becomes, sort of disappears. Let's see if we see one coming up. So you see something, all of a sudden, like, boom. That what's happening there is that the atmosphere is actually interfering with the camera, right? There are some wavelengths in the spectral signature where you can't see through it. You can't see through that particular wavelength because of the atmosphere. Some of those bands are water absorption bands. So there's a region inside in the atmosphere where water is absorbing a lot of the energy, so you can't see any of that information. So this is hyperspectral imagery. So if you hear people say hyperspectral, think of basically different wavelengths of light. So the way they do this is to use a prism and break up the light and then take measurements of those light at the different wavelengths. So, okay. So the disadvantage of spectral imaging is that in order for you to actually be able to get this narrow piece of information, narrow wavelength, you have to make your pixels pretty large. So typically, hyperspectral sensors do not have very good spatial resolution. In other words, you're not going to be able to see the details that you would typically see in a regular camera. So what people do is they actually create a compromise. They'll either use a hyperspectral, they'll use what's known as a multispectral camera, and we'll actually see some examples here of that. So let's open up another set of images and look at some these are known as Landsat images. Right. So what you'll notice is that there's only like 1, 2, 3, 4, 5, 6 bands here, whereas this one had 255 or so, yep, or 224, and it's when you start doing a lot of these types of data collections, it's compromised. So let's actually look at this. Let's create a new display and look at this color image. So we can do now 650, 550, 485, close up. Hold on, I would make it RGB. So let's do that again. 650, 550, 485. Right. So again, very much what you would see from a plane, right? You could see that this is something that you would typically look at. But again, what's most helpful is to put it into color infrared space where we want to see where the vegetation is. So in this case, what you would do is to pick 4, 3, 2. Now when I load that up, it becomes obvious what's vegetation. You can actually see where there is a red, that's vegetation, and the other areas here are definitely not vegetation. You can also click on this and do the same thing we did with the spectral signature. So this is spectral signature vegetation, but these bands do not have as many. We don't have as many bands here. So if we actually do a profile on this, right, you're sort of seeing a sampled version of this. So if I click on vegetation here, okay, you guys see that it sort of mimics this, but you don't have the structure that you would typically do with a hyperspectral image. You don't have that many bands. You only have like about 6 of them, but you still see that similar pattern here. And the advantage of doing multispectral is that you don't have as much data to deal with. All right, there's a lot of data associated with a hyperspectral image. So the format that we have here is what's known as the ENVI format. And it's a little different than what we've talked about. We've talked about PNG, PBM, JPEGs. Net PBM is the one that's a little more close to what this would be. So let's actually look at the data with this. And one thing that I want you to notice is that this image actually has 2 files. All right, this type of image has 2 files. One file is the data, the binary data itself, and the other file is what's known as a header file. In other words, they actually bury some of that information, like number of bands, number of bands, number of lines, number of samples. That's buried into this kind of file, an HDR, this header file. And let's actually look at that. If I say more, Avarice HDR, right? It's actually a text file, right? And you can see that it has the information associated with the this image. It says here that the number of samples is 598, right? 563 lines and 191 bands, all right? And they say that the data type here is 4. And I don't expect you to know this, but data type 4 for ENVI is actually floating point data. Okay, that's very different than what we've seen. Up until now, we've actually looked at image data that is is typically integer, right? This is one of the first ones where we do have floating point data associated with it, all right? Now, one thing that you can calculate with this type of image is the size, and you can actually do a quick calculation on the I already did that. So this image is 598 samples, 563 lines, 191 bands. So if we multiply 598 times 563 times 191, that's how many pixels are in this image. Okay. However, because it's floating point, each pixel is 4 bytes long. Okay. So when we actually look at the data itself, ls minus l avarice dot dat 272.18936, and it's exactly what you got here. 598 samples, 563 lines, 191 bands. That's the number of pixels. Each pixel is a floating point value, so you multiply that by 4. Floating point is represented in 4 bytes of information. If that's not familiar to you. There's a whole methodology of converting those 4 bytes into floating point. And I'm not going to go into it, but if you're really curious, there's an IEEE specification where you have different bit patterns and it can be translated into an actual value. Fortunately, we don't have to do that. Unix actually has the OD function that we've seen that, right? If I did an OD minus BC on this data, it's really not going to make a lot of sense, right? I'm just going to pipe that through more. And you look at that, it's like, oh, hey, it's a bunch of zeros. I'm not too sure what's going on here. A couple of lines, characters. And the reason this doesn't make sense is we're actually misinterpreting this file, right? We know that it's a floating point, but if you didn't know it's floating point, you might do OD minus BC to, to that command. There is actually a floating point option in OD. So if we do this now, we'll find that the values actually make sense, right? You actually have values here that would correspond to the data in the image. In fact, what you really want to do whenever you get an image is not just to look at it and try to figure out all the different characteristics of it. You want to essentially compute the statistics. And the way you would do that is go into basic tools and then just do a statistics calculation just to compute the statistics. And what we can do is we can run that and compare that to what we're seeing with the OD function. So you can generate histograms. There's a characteristic called covariance. We're not going to go into that. Typically, that's in hyperspectral. We talked a little bit about histogram, but let's just stick with the basic statistics, which will output to the screen. So let's actually run that. And it'll go through and it'll tell you what the what those values are. And the numbers that we're seeing here using the OD, is within reason. If you were interpreting this in a different way, these values would probably be would not make a lot of sense. So I can actually, let's actually demonstrate that. Let's see, bytes, W. Minus D. Yeah, so this again wouldn't make a lot of sense. It all depends on the how you're interpreting that that image. So so that's hyperspectral data. Let's go through a couple of more things in here. So the one thing that I always tell people to do is calculate the statistics, because that'll give you an idea whether or not you've got the right information. So there's a couple of other things that you can do. You can do what's known as supervised classification. In other words, you can start drawing regions. In fact, let's actually do a quick demo of that. All right. So let's say that I wanted to classify this image using statistics from a given region. I can actually do that. I can create a region of interest. Let's see, classification. I'll create what's known as a region of interest. Okay. What is a region of interest? It basically allows you to draw a region around an area and take the statistics. So in this case, I'm just gonna, oops. Oh, I know why it's doing that. I need to tell it that we want to take data off of the zoom region. So now I can actually click, 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 close. Oops, I just erased it, sorry. I don't do this often enough, that's why I forgot. All right, so what you've done is you've taken some statistics on a specific region. So we created one region here. And now what we can do is and typically what people would do is they'll collect more data, but this is just showing you how you can select a region and say, give me all the pixels in this image that have this characteristics. So we can say classification, do a supervised, and there's different methodologies. You can do something, this is the simplest one, spectral angle mapper, and you can pick that data, hit OK, and then let's see. Don't mind me, I'm just going to plot windows. Okay. Memory. All right, so let's look at the results. So again, fairly straightforward. All I did is I said I selected this area, and I'm going to see where else in this image do I have that area. So let's actually load that into a separate band. Oh, I think I used the. Oh, I mixed. No, I mixed up. I mixed up the images. Oh, my bad. I selected it for this. Let's actually do that again. Special angle mapper. We wanted this one. Sorry. Then use that same spectrum. All right, so let's look at that one now. All right, yeah, didn't work out too well. But this is, these are things that you have to sometimes mess around with. So unfortunately, even though I selected that, it didn't do a very good job of classification. But these are the kinds of things that you can start experimenting with remote sensing imagery. And as you can see, when you look at the classification part, there's a whole bunch of different factors. And if you're into data science, these types of things are things that you would actually see in data science, the whole aspect of classifying things. This is actually one of the first places I learned about all those algorithms, because what you're trying to do is you're looking at an image and you're trying to, again, if we go back to the what I talked about, one is to detect, two is to identify, and the other one is to quantify. These are the steps that you can use, not just for images, but it's also the same things that you would apply in any sort of data science problem. You want to detect a particular event. You want to categorize that event, and then you want to quantify that particular event. So that's some of the things that you would do here. So let me see what else I have that I can go over really quickly. So we talked a little bit about spectral libraries. You can actually start looking at different types of libraries to see. So let's actually look at some of the spectral libraries that are available here, and open that up. And this just gives you a whole range of different types of materials. So different minerals will have different different spectral signatures. And this is the power of hyperspectral imaging, is that if you can actually compare this to a known set of spectral libraries, you can start being able to identify the different materials on the ground. And this is the actually the promise of remote sensing, to be able to detect different types of minerals on the ground. So the other type of data that you work with in remote sensing is what's known as topographic data. So let's actually take a look at one of those. So this is what's known as a DEM image. Let's go back and open that up. So DEM starts for a digital elevation model, right? And what that represents is how high a given. So if you look at the different pixels, let's actually look at the values of what's on the pixel. You can do a cursor value location, and what this tells you is what is the value associated with the different pixels. So as I move my mouse around, right, you can see that the dark region, 1, 2, 3, 5 in this region. If I go up here, it's much higher, not much higher, but 1, 3, 4, 0. And this is actually how elevation on the surface of a region is expressed as an image. We can, however, actually look at this as a sort of like a wireframe. So we can do a 3D surface view of that region. And actually click on that guy. Let's increase this up so that it'll be a little more dramatic. And this is what this looks like. Okay. Even though you look at this from a 3D perspective, it actually makes more sense to look at it in this way, right, with an exaggerated view. So this is just the surface that we're seeing here. We can actually, let's see, turn off the, trying to remember now. Trying to get to the wireframe representation. I'm not finding it, but this is very important, particularly if you want to understand, for instance, other factors like how does a river flow, where are the areas where vegetation might or might not thrive. So these are things that are represented in image form, but can also represent the different different geometric structure of the ground. So this is what's known as a digital elevation model. So, and a lot of the concepts that we talk about here in remote sensing also applies to medical imaging, right? In medical imaging, you're doing similar things. You're trying to do classification. Is it a tumor or not? All right. You just use different types of energy. You want to know structure. So what is a 3D structure of of a given tumor, for instance, or the surface of your skin? Those are the kinds of things that you would also do. Very much similar to remote sensing. The techniques are more or less the same, just different scales of information. So we won't go into this, but be aware that there is a modality called synthetic aperture radar. So that is basically the same type of radar that you have at the airport, where it's actually figuring out where the planes are. What this does, however, is tries to create an image to show you the distances of the surface of the Earth from a given antenna. So SAR, if somebody says SAR imagery, that's what they're talking about. They're talking about radio waves to do that. Why is that so important? Well, what's the problem with Rochester if you're doing remote sensing? weather, clouds. Okay, there's always clouds in Rochester. If you try to fly and take pictures, you won't see anything. Not so with SAR, with synthetic aperture radar. Synthetic aperture radar can actually see through clouds because it's a different wavelength of energy, right? So because it's using radio waves will penetrate clouds, and you can actually see the structure of the ground in much the same way that you generate the structure of the surface of the Earth through this digital elevation model. Synthetic aperture radar will actually tell you how far the ground is and what the structure is. So this could have been generated by a SAR type of instrument, right? The other type of instrument that, in fact, let's see if I just saw it very briefly here, is LiDAR, right? So LiDAR is essentially like radar, only you use light. I'm going off script here. Let's see if we can find anything, any data that's LiDAR related. Probably not going to work out very well, but we'll try it anyway. So, actually, let me just see if they have any sample data. Let's see. Going off script here. Sorry. Program Harris. Yep. Yeah. That's not gonna. I thought it would work. I didn't test this one out, but LiDAR is another form of image data, or similar to image data. You've seen this with the they use LiDAR a lot in self-driving cars. So also this is what you would see with the Google Street View. Not only do they take pictures, but they also take LiDAR data. So LiDAR data will basically just give you the distances from the sensor to a whatever bounces the light back to you. So those are the things that can that allow LiDAR to do. LiDAR is very good in terms of geometric fidelity, and a lot of the self-driving cars now use LiDAR in lieu of actually of imagery to figure out distances. All right, so that's something that you see quite a lot now in a lot of self-driving cars. Self-driving cars have two methods of trying to determine being able to see a scene, to visualize a scene. One is LiDAR, the other one is stereoscopic imaging. So, or structure for motion is the other term that they use for that. So, let's see, what else do we want to talk about with ENVI? A lot of people have been using ENVI for not just for remote sensing. There is a group that uses ENVI to look at ancient documents, because ancient documents actually have different types of inks on them, and different types of inks have different spectral signatures. So often what they'll do is they'll try to use hyperspectral imaging to determine the difference between overtext. So it used to be, back in ancient days, paper was a very expensive commodity. So what people would do is if they want to create a new book, for instance, they will take an old book that has writing in it, And what they would do, because it's so expensive, it's usually some parchment, is they would scrape it. They would scrape the old ink off, all right, and then cut the book, twist it, and then write over the other region. Twist it and then write a new book on top of that old book. So this is what's known as a palimpsest, and there's actually a lot of these that are around. And one of the more famous palimpsests are the Archimedes treatises, Archimedes palimpsest, and people at RIT worked on that to try to read the undertext of the stuff that was scraped off. And when they actually looked at that, they realized that there was actually some figures and some treatises by Archimedes that people did not know about. Right? In fact, one of the things that that palimpsest showed is the fact that Archimedes actually had the foundations of calculus, way ahead of Newton and Leibniz. Right? They actually found that on the parchment that was scraped off, and in order for them to be able to do that, they actually used hyperspectral analysis to try to understand, to try to enhance some of that imagery that the scholars can look at and say, oh yeah, there's stuff here from Archimedes that actually was not known before, right? So what you're seeing here is a use of tools that was used for one application and then moved over and used for another application of ancient document imaging and cultural heritage. And that's one of the reasons why I'm really into the imaging science part of things, is because you just never know. A solution that you have in one domain can easily be used in another domain for solving some things. So just some of the things I'm teaching you is you never know when you might use it in the future. So there are a couple of things I want to talk about with convolutions and Fourier transforms. We'll hold off on that until the next class on Thursday, because I wanted to sort of make a demo of that. There are a couple of pages that I would like you to look in that book that I gave you on the imaging science of physical imaging of physical sciences, to prepare you for next Thursday, when I actually do a demo on Fourier transforms and spectral, not spectral, but about Fourier transforms, and we'll talk about that a little more, both from the context of ENVI and also image magic. We'll actually talk about what does it mean to take the Fourier transform of an image. What does it mean to do convolutions on an image? And that's a term that you probably hear about, called, you hear it in deep learning, convolution neural networks. What does that mean? All right. And well, the first thing is you need to understand what a convolution is, so that you can better appreciate why convolution and neural networks work really well with images. So it's a term that you probably hear a lot. CNNs is what they're typically called. So let's see. Let me just spend a couple of minutes here to try to go through the different parts here that I want to point out. Decision trees. Let me just make some notes here. I'm going through this. Yeah. I think that's all I want to talk about today. Any questions? Have you guys applied for the CERT account? Have you guys? CERT is the Center for Integrated Research Computing or something like that.
Email you sent out.
Yeah, the email I sent out. Yeah. Please do that in the next few days so that we can start talking about that. We're not going to talk with regard to CERC. We're not really going to talk so much about the image processing as trying to get you to use, a high performance computing environment to do image processing. So that's part of that that exercise that we'll do there with CERC. So let's see, what else do I have? I think that's all I have for today. I'll hang out for the next hour and a half to help you out with any of the exercises. We will not have class tomorrow, but it'll be a good time for you to pick up on getting those exercises in place for me to start grading and looking at. I know that some of you already submitted that, but I know there were some issues with getting the Raspberry Pi to work, so I'm giving you some latitude to do that. Unfortunately, I have family obligations tomorrow, but we'll make that up on some other time for that. But it's a good time to sort of catch up on the different exercises. I also have an exercise that has to do with ENVI, and I will post that up so that you sort of go through that process of trying to use ENVI for your own edification. It's one of those things that you may or may not use in the future, but it's good to actually have gone through it so that you at least have some memory of that process. Any specific questions with hyperspectral imagery? The way I tell people, it's basically just RGB, only you've got more bands. Not that simple, but that's the way to think about it in terms of a data structure point of view. Hyperspectral actually is a lot easier in some respects to do some of the things that you want to do with RGB, namely classification of images. All right, it's much easier because you have so much more information. The drawback is that it's a large data set, so computation is typically an issue. A lot of these images are fairly large, but what it at least does, it gives you some sense of how much data do I really need to get a particular job done in terms of image analysis. So, okay. I would say go ahead and play with the Raspberry Pi to continue with the exercises, and I will post a sampling of the template of a report. Okay. Let me stop the recording and move on. So you had you had issues with the. Let's take a look at that now. Just find my